Welcome back from break, Meridian. Welcome back. The quiz question this break was, what role do anchors serve on the Stellar network? Do they issue fiat tokens, provide a fiat on-off ramp, or both? And the answer is both. Anchors are regulated financial institutions, money service businesses, and fintech companies that offer one or both of the component services. As Tomer pointed out, and someone also asked about it during Jake's presentation, there is such a thing as an anchor that doesn't issue their own asset. But if you want to find out more, check out stellar.org. There's a whole section devoted to anchors. Now, if you run an anchor service or any kind of business on Stellar, or if you're just really into data, which, come on, who here isn't, this next presentation is for you. The dynamic data duo, Debnil Sur, software engineer at SDF, and Isaiah Turner, software engineer intern at SDF, are going to walk you through some amazing work they've been doing to accelerate analytics on Stellar. Debnil, Isaiah, the virtual floor is yours.
Awesome. Thank you for that, Justin, and for running such an amazing conference today. So welcome to Accelerating Analytics on Stellar. We're Debnil Sur and Isaiah Turner. We're engineers at SDF on the Voyager team. We focus on exploring the Stellar ecosystem through data analytics and liquidity, and we're going to be talking about a large portion of that through accelerating analytics on Stellar. So the goal of our work, as well as our team, is to do the fundamental meta work that powers the rest of the network. How do we ensure that assets have robust markets? How do we improve the visibility of the network, both inside and outside of SDF? And how do we use data to further drive network growth? So in this talk, we'll be talking about accelerating analytics at the SDF, specifically going from a low visibility, low observability system to a real-time one. So who are the target audience of this talk? We'd say there are three. First is builders, people who are trying to build analytics pipelines from 0 to 1 to N. I hope our experience is really helpful if you have a bunch of data and you're trying to figure out, how do I do something useful with this? And then how do I scale it? Second, Stellar companies. So as Justin mentioned, if you're building a company, operational analytics really matter, especially if a core part of your infrastructure is pretty young technology. So we're hoping to provide key technologies and context for building out a robust, resilient data pipeline. Third, Luminance as a whole. Of course, since it's Meridian, we want to highlight general progress on the network and at the foundation. So of course, since this is a technical talk, we'll still make sure to highlight key takeaways wherever it makes sense to. So as a brief roadmap before we dig into more, I'll start off with discussing design, the sort of motivation and goals of operational analytics. I'll then talk about the MVP of our system. And then after that, I'll hand over to Isaiah, and he's going to discuss the real-time approach that we then took. And then finally, we'll talk about some use cases, some of the really exciting stuff we're doing and things we're thinking about. So let's start with design. I'll talk about our motivation, goals, and some key technical decisions. So to understand design goals, let's first discuss why you even want a cloud scale data pipeline. So you'd like to quickly and efficiently generate histories of assets, accounts, markets, whatever on the network. The primary use case for this, of course, is internal business analytics. We have to make it easier for our business development and ecosystem teams to understand the effects of their efforts. So Stellar uses the widely used database system Postgres. It's been industry standard for about 25 years. Stellar Core writes data to it, and Horizon uses Stellar Core data, but also has its own Postgres tables. The pros of this are that it's well-known, well-documented, really good for online transaction processing when you have a lot of writes and reads, highly concurrent environment. The cons are that it's slow for historical queries for a specific column value. It's decidedly worse for analytics. So in particular, Horizon's database structures and indices are optimized for the exposed web API, but doing deeper queries across different accounts or tables can become highly inefficient. So for example, complex joins and filters become really time inefficient unless you have indices. So to quickly understand behavior at scale, we realized we'd likely have to build new infrastructure to avoid slowing down the entire Horizon API. So now we've talked about motivation. What are the goals when you're building the actual system? So above all, and you'll find both of us emphasizing this, is value for internal stakeholders. When you're building data product, it's really easy to nerd out and just build something cool. But the end user is almost always your non-technical users. So if product guarantees don't align with business needs, you're not going to ship the right solutions, and you might just create more work for everyone. Second, open source or open access. So open source is really core to SDF's DNA, and we want to support open source tools wherever we can. Obviously, some things like cloud infrastructure require spend, and there we want to make sure that anyone in the organization can use it, and it's really easy to flip the switch and make it public. Third, daily updates. Some businesses need real-time updates, but when we were starting out, once a day was sufficient. I'd like to flag this as a key distinction from V1 to V2, and Isaiah will talk more about this. Fourth, there has to be really easy integration with your current stack. So obviously, I've talked about the importance of Postgres, but also it has to be able to be run and administered by whoever your in-house operational team is. So our in-house operations stack uses Docker and Kubernetes. Docker is software that lets you contain custom programs in an environment, and Kubernetes is orchestration software for deciding how these containers are deployed and run. So obviously, it has to be really easy for our operational folks to pick it up and run with it. And finally, easy metrics and visualization. As we've talked about a few times now, it's got to be really easy for anyone to just pick this up and generate graphs, charts, whatever they need for their own use cases. So a lot of those requirements are fuzzy. How do they break down into core technical decisions? So I've organized some of these tools from most to least defined. So the deployment infrastructure would be Docker and Kubernetes for orchestration, cron jobs, whatever. Then additionally, there'd have to be some kind of cloud scale warehouse for easy Postgres, scripting, authentication, and finally, metrics and visualization. This is the least defined. We'd like this to be open source, free, and easy for non-technical users. So with all that said, let's now talk about our minimum viable product, our MVP. And I'll discuss the implementation details of the first version of our system, nicknamed Hubble. So let's talk about infrastructure. This decision was made for us, but some of those details made everything a lot easier. Docker-based containerization gave a key standard for evaluating other tools, especially visualization. Could it be deployed by our team on our infrastructure? Kubernetes cron jobs also gave a really easy method to run these Docker deployed scripts. So we could just set a schedule and then run various procedures. It was super easy to connect the existing Postgres cluster. It was also really easy to provision storage volumes if we needed external memory to run the data pipeline. And it also allowed for retry on failure. Second, for a cloud data warehouse, we chose BigQuery. I was initially pretty worried about this. There's a lot of options, but it was just a lot better than anything else. The queries were super fast, 10 to 1,000 times faster than anything from Horizon. We were just blown away by how fast it was. Second, the native cloud storage integration. Where do files live during the pipeline? Google Cloud has a cloud storage service called Google Cloud Storage. So this let us separate the pipeline into export tables from Postgres onto disk, upload from disk to cloud storage, and then upload from cloud storage to BigQuery. Splitting up our long pipeline into a few components reduces the risk of failure, and it makes retries much less expensive. Third, there were painless command line utilities. Super easy to script exporting files from Postgres, then uploading them to BigQuery. That makes creating a basic pipeline easy to reason about and also easy to containerize and deploy. Fourth and finally, Google Suite authentication. So we use G Suite inside SDF. So it was easy to get started with BigQuery and share those permissions across the organization, a core part of the open access I talked about before. Third layer is one of metrics. This was pretty straightforward, honestly, once we had made the decision to use Docker at the bottom and then Google BigQuery on top of it. So we wanted some basic data science capabilities slightly outside the scope of what SQL can do. And after talking to folks around the org, we realized that surfacing these as spreadsheets made a lot of sense. It provides a common language for non-technical folks, and it also keeps data tabular and easily downloadable. So Python scripts are honestly a Swiss Army knife for data. They can read a table from BigQuery, run some custom post-processing using some block explorers like Stellar Expert, and then write the ultimate outputs to a Google Sheet. It's also cool to note that we deployed these on Google Cloud Scheduler, and then we could run them in a serverless fashion. So once the BigQuery dataset was updated by our cron job, these scripts were triggered and then update our spreadsheets. Really cool, easy end-to-end flow. One of the things that happens when everything's within the sort of same cloud stack. So fourth and finally, visualization. This is actually the hardest part of this project because there's a million tools and documentation comparing them isn't very easy. So at this point, we settled on BigQuery and Google Sheets. So we wanted pretty easy BigQuery integration. We also need easy deployment through Docker and Kubernetes, and nice visualizations through either drag and drop in SQL. And of course, if you can get all of that through open source, even better. So I tried a lot of different tools. Google Data Studio, Apache Superset, and Looker were all particularly strong too. But we found that there was a fundamental trade-off. If it could work with BigQuery, it usually either didn't have drag and drop or it just wasn't free. So we ended up settling on Metabase. It has drag and drop interface as well as SQL. It's also free and easy to set up. I think if you need to MVP a pipeline, it's a phenomenal option. So a lot of things are good. What are some of the downsides of V1? Why was there even a V2? So first, daily frequency is slow. It's definitely sufficient for initial use cases, but a daily update limits building out data-intensive applications on Stellar. So we'd like to get closer to real-time updates. Second, observing, let alone fixing failures is hard. We were still learning our way around Kubernetes logging, and we wanted to retry specific portions of that pipeline before that failed. So task management systems, like Isaiah will talk about, are a natural evolution of the system using modern data tools. Third, our visualizations were all private. We'd love to expose our information publicly, but we can't really mix the platform we use for internal business analytics with the rest of the world. So we decided we'd have to think about a good intermediate solution. Fourth, exploring data is pretty hard. You'll notice I haven't talked about a data science platform. And so while our serverless functions provide some capabilities for robust regular jobs, ideally we'd be able to enable exploratory data analysis via scripts, like a Jupyter notebook. So of course, that's a lot of things we could build. How do they connect to the goals we initially set? So you can see here that our goals start to change. Update rate of daily is nice. Can we get even faster? We also realized that Postgres was table stakes for most tools, so it became less of a priority. And for a deployment side, some partner needs implicated this, and Isaiah will talk more about different ways you can deploy a better system moving forward. So in terms of modernizing, that gave us three things to do. First, observability first. This was paramount for us in designing V2. If we want to operate at faster speed, it's got to be easier to debug. Second, the faster update rate. Mentioned that before. It became a pretty clear place for us to focus and get better. But third, we also realized that data science didn't matter as much. There's pretty limited engineering capacity for data stuff. There's a lot of other things going on at SDF and on Stellar. So we realized we wanted to focus on the problems that gave immediate value to our users. And it seemed like updating more regularly was the thing to focus on. So all that in mind, I'll hand it over to Isaiah.
Hey, I'm Isaiah. So the primary goal of our V2 data pipeline was to increase the frequency of updates from daily to near real time. In order to meet our goal, we had to break the pipeline down into several core pieces. The first piece is the Stellar ETL, which extracts data from the history archives and from Stellar Core. So the Stellar ETL is a command line interface written in Go. We decided to use Go because it integrates well with our existing tech stack, which is written in Go. Go is also really fast and it's easy to maintain, so we felt it was the best choice for the ETL. ETL stands for extract, transform, and load, and the Stellar ETL does exactly that. It extracts data from the history archives using the New Horizon ingestion system, transforms it into JSON that is compatible with BigQuery, and then loads the data into a text file. So with the Stellar ETL, you can run a simple command like the one below, and get all the operations that happened from ledger 1000 to 1010. The ETL is a very powerful tool for getting historical data. So I mentioned that the ETL uses the New Horizon ingestion system. This new system uses the history archives instead of Stellar Core and the Horizon databases. The history archives are more consistent and developer-friendly. It's also much easier to access data using the history archives. One important thing to note is that new data is loaded into the history archives every checkpoint ledger, which occurs about every 64 ledgers. Since the average close time of a ledger is 5 seconds, this works out to about 1 checkpoint ledger every 5 minutes. As a result, we targeted 5 minutes as our update interval for our data pipeline. So there were a few challenges that came up when I was developing the Stellar ETL system. The first is that the ingestion system was still in development while I was working on the Stellar ETL. This meant that at times new functionality was being added or existing functionality wasn't fully documented. For example, at one point, I didn't even think it was possible to get accounts, offers, or trust lines because the method to get them wasn't as well documented. It was also occasionally a challenge to replicate existing table schemas. We didn't want to lose any information, but sometimes we weren't able to get part of the schema using the ETL. For example, the V1 tables have timestamps that indicate when a row was added to the Horizon database. We weren't able to access that information since we don't use Horizon. So in this case, we just chose to omit the timestamps. The third and largest challenge is that the history archives could provide some of the data that we wanted, but it didn't contain information about ledger entries like accounts, offers, or trust lines. In order to get that information, we had two choices, the bucket list or Stellar Core. The bucket list is a data structure developed by the core team, and it's located in history storage. It's a complex data structure, but essentially it stores hashed ledger entries. It can be used to get the current state of accounts, offers, or trust lines, but only at checkpoint ledgers. We wanted to get a ledger by ledger amount of information, so we had to use Stellar Core. Unfortunately, starting up a Stellar Core node takes a while, which would slow down our data pipeline later on if we had to create a new instance of Stellar Core for each of our 5-minute update intervals. Our solution was to create a long-running Stellar Core instance that constantly exports accounts, offers, and trust lines as the network progresses. In order to keep a long-running Stellar Core instance, we used the captive core functionality that was part of the new Horizon ingestion system. Captive core captures a Stellar Core node, runs the node, and then decrypts the data that the node receives. The ETL is then able to read in the decrypted data, transform it, and export it. So the Stellar ETL is as complete as software gets, and you can check it out at the link provided. So now let's move on to the second part of the data pipeline. We used Airflow for this second part. Airflow is an open source task management system written in Python. It was open sourced by Airbnb a few years ago as a generic task management system, and it has become one of the most popular and most used tools across the industry for data science workflow management. We chose to use a well-established tool rather than rolling our own tool. So in Airflow, the user defines directed acyclic graphs, or DAGs, which act as complete workflows. I'll use the word workflow to refer to DAGs in this talk. So in Airflow, users define the tasks that make up the workflow. Each task has an operator type. For example, if you wanted to run a Python function as a task, you could use a Python operator. To run a bash command, you could use a bash operator. There's a wide variety of operators, which makes Airflow very versatile. Once a workflow and its tasks have been defined, the user can set the workflow to run on a schedule. Then Airflow handles all the internal work, like scheduling tasks or retrying failed tasks. Note that unlike our V1 system, this is a component by component process. This means Airflow can retry individual tasks that failed instead of restarting the whole pipeline. One additional benefit is that Airflow, instead of exporting data from the beginning, you can export within time ranges. Airflow also has a really detailed logging system and a nice UI. The picture on the right is an example of the Airflow UI. You can see all the workflows on the left. You can also enable or disable workflows, see their schedules, and easily identify failed or successful runs by looking at the numbers within the red or green circles. So once we decided that we were going to use Airflow for task management, we needed to integrate our existing work into it. Airflow workflows and tasks are written in Python, while the Stellar ETL is written in Go. We wanted the Airflow setup to be usable on any system that had Airflow, so we needed some way to get the Stellar ETL onto the system too. We decided to use Docker, because Docker images are incredibly portable. Airflow also has a Docker operator, which can pull Docker images and run commands on them, so the Docker integration was handled for us. We decided to use Docker over something like installing the Stellar ETL binaries because the Docker image could ensure that we had all the dependencies for the Stellar ETL and for the captive core instance in one place. Then we use the Google Cloud Storage API in order to upload exported information into Google Cloud Storage. Finally, we used an Airflow operator called Google Cloud Storage for BigQuery in order to complete our data pipeline. The workflow for the history archive export process is displayed below. We also have a workflow that starts the long-running Stellar Core process and another that senses when new batches are exported and uploads them. So again, the Airflow setup is as complete as it gets, and you can check it out at this link. So like any technology, Airflow has upsides and downsides. Let's start with the pros. Airflow handles scheduling and retrying tasks, which is a significant amount of work that now we don't have to worry about. It also has detailed logs and a good UI, so we can easily get information about the workflows and their status. Airflow provides fault tolerance and logging, which was one of the initial motivators for a V2 system. It's also really easy to add new workflows and tasks to Airflow in the future. However, there are some downsides. Airflow works in time ranges while Stellar works in ledger ranges. As a result, we have to search for the ledger associated with the time. This adds some extra calculation overhead and added development time. Airflow also is going through a major update. The current version is 1.10 and the next major release is 2.0. 2.0 isn't available yet, but in the Airflow documentation, it's not always clear which features are 2.0 exclusive. So during development, there were often times when I thought I would be able to use the function, only to find out that it was only available in 2.0. In these situations, I usually ended up creating a custom operator that was identical to the 2.0 operator. Now let's talk about moving the setup into a production environment. There are two main paths we considered for deploying Airflow. The first is a custom Kubernetes setup. So in a custom Kubernetes setup, the developer defines and configures the pieces of Airflow that fit into the Kubernetes setup. So in general, there's a few main components that should always be included. You will always need to define deployments for the Airflow scheduler and web server pods. You also need some way to provide those pods access with your workflow definitions. You can place your workflows in a persistent volume that's mounted on the pods, or you can sync the pods with the Git repository that contains your workflows. Once you have the scheduler and web server, you need to define a database that Airflow can use to store data on the backend. You also need some separate storage space for all the logs that Airflow will generate. In order to actually run the tasks, you have two main choices. You can define an Airflow worker pod that will run tasks and use Airflow's Celery executor, or you can use the Kubernetes executor. The Kubernetes executor runs each task in its own separate Kubernetes pod. So as you can see, there's a lot of different moving parts to this setup, but fortunately, there's existing Helm charts online that provide the core backbone for the setup and that you can tweak in order to fit your own needs. The second potential path is Cloud Composer. Cloud Composer is a Google service made specifically for deploying Airflow. Cloud Composer provides a working Kubernetes setup that is integrated with the Google Cloud environment. So the Airflow web server, scheduler, and worker pods can all run in the cloud and use a common cloud database. Cloud Composer has really strong Kubernetes integration. It provides the scalability and power of Kubernetes while freeing developers from having to create the config files manually themselves. So let's go through a quick comparison of the two options. In your own custom Kubernetes setup, you have to set up the configs and databases and everything that Airflow needs yourself. Cloud Composer, on the other hand, does all of that for you automatically. It handles the database that Airflow uses and provides the config files for all the pods for you. However, that convenience comes at a loss of flexibility. For example, Cloud Composer worker pods don't have very good Docker support. They don't have Docker installed by default, so we had to edit the config files in order to ensure that they could run the Stellar ETL Docker image. It's also difficult to write files directly into the shared Airflow worker pod storage space. So I had to write a separate script that moved local files to shared storage. If you have a custom Kubernetes setup, you can ensure that workers have access to Docker. You can also ensure that your shared storage is configured for direct writes. You aren't as restricted to the Google ecosystem with your own custom Kubernetes setup. That extra flexibility means that you can find ways to cut down on costs. Cloud Composer, on the other hand, makes you pay extra for that added convenience that it provides. So now that we know how the data pipeline works, let's go over some of the applications. Our previous data pipeline didn't allow us to store historical order book data. We stored the current offers that were on the market, but there was no way to get the state of all orders at historical ledgers. With the V2 data system, we can get historical order books and store them in a compact manner. This allows us to calculate metrics like liquidity at historical ledgers. Once we can calculate liquidity, we can get an idea of how healthy different markets on Stellar are, as well as identify market makers that may be interested in partnering with us. Another potential application is storing historical account balances. A financial app built on Stellar could use the balances to provide a user with a historical view of the contents of their wallet. The V2 data pipeline is also potentially useful for external users. Stellar users can check out the public data set, and now it's more up-to-date and fresh. In addition, external developers can use the dataset as a source of truth because now it is in a real-time manner. So finally, Debna talked a little bit about the data science platform. So while we haven't expanded the data science platform yet with the V2 system, doing so now provides a significant amount of value to users. A data science platform could pull data from the new data pipeline and process it. Since the data is more up to date, the platform can be used for decision-making as well as historical analysis. If anyone out there is interested, please feel free to reach out to us.
Great, that was fantastic. And there are a lot of questions coming in. And I think, well, first of all, just thanks so much for sharing that. It's really interesting to see what you built, to see the thought process behind it, and to see like the results and what you can start to do with them. I think the first question, we only have about 4 minutes for questions. So I think the first thing is, let's say someone does want to find out more. What's the best, or get in touch with you? What's the best way for them to do that, just in case we run out of time?
Just tweet at me or reach out to me at debnell@stellar.org. And I think if you want to set up either of these, the 2 links that Isaiah shared are both fantastic. Would recommend checking those out. Great.
So what would it take for someone to set up their own version or their own ETL, like to start?
So go for it, Isaiah.
So the Cloud Composer setup is very simple. The README that we have for that repository is very detailed. And so it should walk you through all the steps that you need. You will need to have your own Google Cloud account, and you'll have to set up payments and things like that so that you can fund the ETL process. But the actual steps of setting it up are all available in the README.
And it sounds like you can customize what you're doing pretty easily for your use case. Is that correct?
Yes, that is. So we used it for our own ETL process, but Cloud Composer in general is really good for setting up any Airflow setup in Google Cloud environment.
Great. Someone was asking whether Hubble takes advantage, and I think you answered this in the presentation, but whether it takes advantage of the fast core or the captive core that Eric was talking about yesterday in his presentation. And can you just explain a little bit how it does?
Yeah, so it definitely does. It uses the captive core in order to get accounts, offers, and trust lines. So those are things that we can only really access using either the bucket list or captive core. And so captive core is our preferred method because it provides a more granular view of the information. So essentially, we just run a captive core setup. Because of some of the things that Eric mentioned yesterday, it's a very fast catch-up process. And so as the network progresses and different accounts are added or deleted or changed, then we can retrieve all of those changes from the captive core node and then transform them like normal in the ETL, and then export that data.
Great. And I guess finally, there's sort of a set of questions, but they all relate to what's next. You've sort of gone through the MVP and through V2. What are the plans to move forward after this?
So next big thing, as I've touched on a couple of times, we want to figure out how do you enable exploratory data analysis on this as one, and then another, how do you visualize this information more easily? So things like really easy public dashboarding around the state of current markets or assets or transactions histories. So those are the sort of two directions we want to take it in. One is just make it easy for anyone to sort of roll their own analysis. And the second is just really good public dashboarding.
Great. And what kinds of things can you imagine building dashboards for?
So you could imagine, let's say somebody is just a business attempting to build on Stellar, right? And then they're thinking, oh, what does it look like in terms of volume coming in and out of Nigeria? Or is there an opportunity for me in the Philippines, right? So you can imagine with all this on-chain information, we now have the ability to see how these markets have evolved over time and how they're looking and how specific corridors are looking. So you can imagine that all of these are things that on-chain information provides to you, that if you can query in an efficient manner, you have really good visibility, but you also don't have to trust anyone else. You don't have to rely on the idea that anchors are being truthful to you, even though there's no reason they wouldn't be. But now you have some public information that you can quickly query and ask that question.
Amazing. Well, thank you so much. I mean, I will say that over the past few months, I've been using some of the tooling, like you've built out some resources for us to explore internally, and I've played with a lot of them. I've been able to find answers to super complex questions really easily. And it's really amazing to have that sort of power. It's just so much power. Thanks so much.